we in now? Okay, I don't know what the heck I did. I might have started the wrong thing. So, as I was saying, Thavinin's theorem states that any two-terminal linear circuit can be simplified to a practical voltage source equivalence. Containing a voltage source VTH and resistance RTH. The voltage VTH is the open circuit voltage of the live circuit, and the resistance RTH is the resistance seen looking into the dead circuit. So for a very, very simple circuit, let's say that we have apologies. I will not, my stylus right. Trying to remember something I gave you guys on the exam, where you probably used source transformation to solve it, but we can easily solve it using Thevenin and Norton equivalent circuits as well. So let's say that this is a 3 amp source, this is an 8 volt source, this is a 2 volt source, this is 10 ohms, and this is 6 ohms. And I'm going to call this guy terminal A and terminal B. Okay. So if we wanted to find the Thevenin equivalent circuit for this guy specifically, we would need to determine two quantities: the Thevenin equivalent voltage and the Thevenin equivalent resistance. So based on the fact that I gave you the definition for both of those quantities, what should we do to find the Thevenin voltage? Thoughts? Benjamin. So I'm not sure what you mean by that. So the Thevenin voltage is by definition the open circuit voltage, right? So if we want to find the Thevenin voltage seen between terminals A and B, it is literally just the voltage drop across the open circuit terminals. So that's what an open circuit voltage is. The voltage drop across a pair of open circuited terminals. So how might we determine what that voltage is? There are a multitude of ways, okay? One way would be to do a source transformation and then apply Kirchhoff's voltage law, okay? I'm not going to do that. It's too easy. Well, actually, I don't even know that it's too easy, okay? So let's think about this thing rationally here. We have a circuit. with a couple of voltage sources in there connected to an open circuit and stuff, right? So what's the voltage drop over the 6 ohm resistor? By inspection, not Ian. Yes, the voltage drop over the 6 ohm resistor. Let me specify things a little bit better here and say the voltage drop with this polarity.
How it is right now.
Exactly with the circuit how it is right now. 0. Why? Exactly right. Because that resistor is not connected to a closed current carrying path, the voltage drop over it has to be 0 volts. What is the voltage drop over the 10 ohm resistor? Six? I disagree. How did you get 6? Okay. So how much current flows through the 10 ohm resistor? I disagree. I disagree with the answer none as well. So let me rephrase my question. That 3 amp current source is driving 3 amps of current in this circuit. Where's literally the only place that 3 amps of current can flow? Through that 10 ohm resistor, because the rest of the circuit is open circuited, right? So I would argue by applying just good old Ohm's law and looking at this circuit critically, we can see that there is a voltage drop of 30 volts with this polarity, right? The 3 amps of current as it comes down here cannot branch off to the right because no current can flow through that open circuit. So all of it must flow through the left through the 10 ohm resistor. Does that seem like a reasonable assessment of what's going on here? All right. So what's our Thavinin voltage? So 8 plus 30 minus 2, 36. Absolutely right. Solved using only information that we had on the first 2 days of class. No source transformation, no tricky crap or anything like that. Just looking at our circuit and gleaning what small pieces of information that we can, and then applying our fundamental concepts, okay? So we figured out what our Thevenin voltage is. And again, that's done with a live network, meaning that all of our sources are left on. When we determine our Thevenin resistance, we have to be looking at a dead network, which means all of our independent sources need to be, turned off. So what should that network look like? How do I turn off my current source? Open circuit, all right? So I'm going to have an open circuit here at the top. There's my 10 ohm resistor. How do I turn off both of my voltage sources? Short circuit, right? Or replace it with a wire. Equally valid. So here are both of my, oops, I forgot to put the 6 ohm resistor in. So this circuit, or network, or whatever you want to call it here, technically it's both because it does have a closed current carrying path. Well, actually it doesn't because everything's open circuit. So I guess it is a network from the fundamental definition. Has 2 open circuits. How do we determine the Thevenin equivalent resistance? We need to be looking into the same set of open circuit terminals that we were looking at when we determined the voltage, right? So we're going to look in through that same terminal pair AB. So what is our equivalent resistance? Pardon? Absolutely. For resistance, absolutely not. 16 ohms. 10 ohms in series with 6 ohms, right? So we have 16 ohms here, which means that our equivalent network for our original relatively ugly looking circuit is just this guy. From the perspective of a load that is connected across those terminals A and B, where that load could be a resistor, a capacitor, an inductor, some combination thereof. It could include sources and all other kinds of crap like that. Okay, does not matter. But from the perspective of some load, it doesn't see those three sources with those two resistors. It sees this guy. They are electrically equivalent, meaning they deliver the exact same amount of voltage. That network delivers the exact same amount of current and therefore supplies the exact same amount of power to whatever network is connected to those terminals. Okay, so that's Thevenin. Now let's talk about Norton real quick. Norton's theorem states that any two-terminal linear circuit can be simplified to a practical current source equivalent. Containing a current source I Norton in parallel with a resistance R Thevenin, right? So technically, it's in parallel with a resistance R Norton, but the definition for R Norton and R Thevenin are identical, so you actually never see R Norton anywhere, okay? So the rules for determining the Norton equivalent resistance are exactly the same as the rules for determining the Thevenin equivalent resistance. All right. So this current source I Norton is the current flowing through the short circuited terminals of the live network. Okay. So I'll redraw this. We had a 3 amp source directed to the right. This was a 10 ohm resistor. We had our 8 volt source here. We had a 2 volt source here. Here's terminal A. I'm going to remember to draw this dang 6 ohm resistor this time. Here's terminal B. So if we wanted to find the Norton current. Alan. Yeah, apparently I can't look at both pages at the same time, so I'll let you guys copy this real quick. Yes. Probably using slightly less words because you should have seen this before, but yeah. Let me know when I'm good to scroll down. All right. All right. So how do I determine the Norton current? What do I do to this network? Short circuit the terminals, right? The Norton current by definition is the current flowing through these short circuited terminals. So I draw a wire, and then this current is going to be my Norton current. So how could I go about finding my Norton current? So when I am finding Thevenin voltage or Norton current, I need to be looking at the live network, which means all of my sources need to be on. Only when I am trying to determine the Thevenin resistance do I look at a dead network where the sources are turned off. Yeah.
I mean, the easy thing with combination is typically have 3 volts in series, but also for an alternate, INO is the current for the 6 ohm resistor. So if you basically the same way we did the last problem, the Thevenin part, find the voltage across that resistor divided by 6 ohms, you'll have INO.
Yeah. So I can't just look at the portion of the circuit that contains the 8-volt source, the 2-volt source, and the 6 ohm, because that's not a complete path, right? There's a 10 ohm resistor in between there that we have to pay attention to as well. Right. So yeah, the Norton current does flow only through the 2-volt source, the 6 ohm resistor, and the 8-volt source. That is correct. Yeah, so let me ask you guys a question. Can we look at this guy and say definitively that the voltage drop over the 10 ohm resistor is going to be 30 volts this time? No, because now that 3 amps of current can branch off because there is a closed path to the right, okay? So the answer to how we could determine this current I Norton really is however we are comfortable with. So what Ian suggested, which is perfectly reasonable, would be to do a source transformation here, yielding us a single loop circuit that we could easily apply Kirchhoff's voltage law to and Ohm's law and find the only current flowing around the loop, which would have to be the Norton current. Or we could take a look at this guy and say, you know what, it's only 2 meshes, so I could do mesh where one of my currents is known, so that seems like it's not a whole heck of a lot of work either. Either of those routes are really solving the problem in practically one step, right? That's one way to do it, sure. So if we did the source transformation route, we would have our 8-volt source. We would have our 30-volt source. We would have our 10 ohm resistor. We would have our 2-volt source. Here's our Norton current. I Norton. Here is our 6 ohm resistor. And if I start here, I'm going to have -8 volts, -30 volts, plus 10 ohms times I Norton, plus 2 volts, plus 6 ohms times I Norton is equal to 0, which means I Norton is 36 volts over 16 ohms. So gosh, let's see, that's going to be 18 over 8 is 9 over 4. That's one way to do it. Another way that we could approach this, it's roughly the same level of difficulty, would be to just write a Kirchhoff's voltage law equation around this loop, right? So I could say that -8 volts plus 10 ohms times I Norton minus 3 amps plus 2 volts plus 6 ohms I Norton is equal to 0. Where I'm applying mesh, except that only that current in red, which is my Norton current, is the only unknown quantity. It's literally the exact same math we would get. It's distributing that 10 ohms times that 3 amps. Right? So whichever way clicks up here for you better is what I would argue should be the approach that you take. Right? What makes sense to you is probably going to be the most beneficial to you. Yes. So are the 30-volt source and the 2-volt source still in series, even though there's a resistor between them? Absolutely. So let me explain this, okay? So on the very first day of class, when we were talking about whether things were in series or in parallel, I said that 2 elements were connected in series if there was a single point of interconnection between them, a node, with no branching paths, okay? Now, you could easily argue that that's not true here, right? Because the 30-volt source and the 2-volt source don't even touch each other. So how could they be connected in series? An alternative definition for things to be in series is that they're carrying the same current, right? That's comes from Kirchhoff's current law. So if we think about it, this current I Norton is flowing through the 30-volt source. That same current is going to flow through the 10 ohm resistor. That same current is going to flow through the 2-volt resistor. That same current is going to flow through the 6 ohm source. That same current is going to circulate up and flow through the 8-volt source. So they're in series because they're all connected in such a way that the current never has a chance to branch off. Okay. So we can look at a series connection from the perspective of literally how the elements are connected, or we can look at it from what that statement really means with regards to the behavior of the electrical quantities that we're interested in, right? So a series connection forces the same current to circulate through all of the elements, which means in this case, if I move the elements around, as long as I maintain their polarities, the order of them doesn't make any difference whatsoever. Right? So we can leave them as is. So for instance, when I did my source transformation there with the 3 amp source in parallel with the 10 ohm resistor, and I changed it into a 30-volt source in series with the 10 ohm resistor, did it remotely matter if I put the voltage source on the left or the voltage source on the right? Doesn't matter, as long as I get the polarities correct. So I could have redrawn that with the 8-volt directly connected to the 10, connected to the 30-volt source, connected to the 2-volt source, and it would behave in the exact same way. So those two things are electrically equivalent, which means it doesn't matter which representation I use. Exactly right, yeah. So while they're not, this element is directly connected to the next one, they would be considered in series because the current has no other path to take. All right, so we don't need to look at the Thavinin resistance for this guy again because we've already done it. So this is Thavinin and Norton equivalent circuits when we don't have any dependent sources. So the goal for today is to talk about Thavinin and Norton equivalent circuits when we do have a dependent source, all right? So let's say that I have a 10-volt source, a 5-ohm resistor, a 3 VX current source, a 20-ohm resistor. Here's terminal A. And here is terminal B. And I'm going to say my voltage Vx is that open circuit voltage. So if I want to find the Thevenin equivalent for this guy, what do I need to do? Find Vx. Vx and Vth represent the exact same quantity. So how can I do that? Okay, so let's approach it using mesh. Which mesh are you speaking of? Because I would argue that there's only one, right? Okay. So applying mesh here really isn't mesh at all. It's just Kirchhoff's voltage law because there's only one current flowing through things. Everybody understand that, right? There can't be a mesh current on the right-hand side because there's an open circuit there, so we know that no current can flow through it. So if we apply Kirchhoff's voltage law around this loop, what we get is negative 10 volts. And then I'm going to call this mesh current IA for right now. We're about to run into an issue. And then what comes next? Rumbling from this general direction. I would like to hear what you guys said. Nobody over here answered my question. 5 times IA. Yes. Oh, yeah. Okay. So what comes after that? Any thoughts? Okay. So that's a reasonable thought, but it's incorrect. The reason that it's incorrect is because 3Vx is a current source, right? The arrow indicates that it is a current source. So the problem that we're running into here, when we try to apply Kirchhoff's voltage law to this, is that it includes the voltage drop over a current source, which is a problem when we're trying to do mesh analysis. So we need to think a little bit, okay? So let me ask you guys a question. This is a question that's going to get asked a whole heck of a lot when we're finding open circuit voltages and stuff like that, okay? What is the voltage drop over this 20 ohm resistor? 0 volts, because there's no current flowing through it. So what that means is that the voltage drop across that current source is 1 Vx, right? Because we could write a Kirchhoff's voltage law equation that says, let me prove this to you here for those of you that may seem incredulous. So I'm going to call this VCS. So if I write a Kirchhoff's voltage law equation around my right-hand loop, I'm going to have negative VCS plus 0 volts plus Vx is equal to 0, which means Vx and VCS are the exact same quantity, right? So effectively, we can move that voltage Vx down to the current source because they're behaving as if they are in parallel because there's no voltage drop over the resistor, all right? So I did a KVL around the right-hand side and found that the voltage drop over the current source has to be exactly equal to that voltage Vx. With practice, you won't have to do the Kirchhoff's voltage law. You'll just see, okay, so if no voltage drop occurs over this resistor, then I can just say Vx kind of move down the circuit a little bit, all right? So that allows me to put plus Vx here and set this guy equal to 0. So what's IA? Negative 3 Vx, right? We had that, we're applying mesh, so we need that current relationship as well. So what we wind up having is negative 10 volts plus 5 ohms times negative 3 Vx plus Vx is equal to 0, which looks like negative 15 Vx plus Vx, or negative 14 Vx is equal to 10 volts. If my algebra is correct, if it's not, by all means, tell me. And Vx in this case would be 10 over 14, I mean negative 10 over 14 volts. Which has to be the exact same thing as our Thavinin voltage. Questions, comments, concerns about this one? Anybody got anything? Yes.
So you got IA from when you got negative 3Vx.
It's going in it's the same current, but representing the same current, but in the opposite direction. Absolutely right. So effectively, if I'm doing mesh, any current source I have, I am going to need a current-based relationship, right? We could consider this current source to be on the perimeter of the circuit because it's the only, there's no opposing current to it, right? So even though, like, this guy were short circuited, it's an interior current source and we have to do around the outside loop, right? And we're about to do that because let's talk about now the Norton current, okay? So we figured out what our Thevenin voltage is for this guy. Okay. All right. Yes. Will there be a voltage drop over the 20 ohm resistor? No. because it's not connected to a part of a closed current carrying path, right? The current that can flow through an open circuit is exactly 0 amps. So since 0 amps flows through the 20 ohm resistor, from Ohm's law, the voltage drop across the 20 ohm resistor has to be 0 volts, right? So anytime we have an open circuit like that, like let's say just for the sake of argument here, that we weren't paying a whole heck of a lot of attention and we tried to write a mesh equation for this guy. By inspection, we could see that this mesh current IB has to be 0. So we could make the mesh work in that way, right? We could make it behave more like, I guess, a traditional mesh circuit where we have a super mesh because there's an interior current source and we apply both meshes around. So just to recap my statements there, because there is no current flowing through the 20 ohm resistor, and that occurs because it is not part of a closed current carrying loop, there cannot be a voltage drop across the 20 ohm resistor. That's what allowed us to recognize that Vx is the exact same thing as the voltage drop over that dependent current source, which was a critical piece of information that allowed us to solve this thing. Was that remotely helpful? Okay. So Norton current. We have our 10-volt source. We have our 5 ohm resistor. We have our 3Vx dependent current source. We have our 20 ohm resistor. Here's terminal A. Here's terminal B. Here is our voltage Vx. So if we want to find the Norton equivalent current, what do we need to do? Not Ian. Short circuit those terminals, okay? And this current is our Norton current. So let me ask you guys a question now that will be critical to our analysis here. What is Vx? Pardon? 0. Why? Caleb, I think. Caleb Redford. He's a nanosystems engineering major. I'm studying up on you, buddy.
It's not.
Right. So it has everything to do with the fact that it's the voltage drop over a wire or the voltage drop over a short circuit, which by definition has to be 0 because it has a resistance of 0. So Ohm's law says that for any amount of current flowing through that 0 resistance, we get a 0 voltage drop. Okay. Excuse me. So if Vx is 0, what is that current source behaving as? An open circuit, right? If the current flowing through the current source is 0 amps, then it's behaving as if it were an open circuit. So what should our Norton current be if we are treating that interior current source as, pardon? 10 over 25, right? So let me recap that for you, all right? We were able to determine by inspection that Vx is equal to 0 volts. Everybody okay with that? Voltage drop over a short circuit has to be 0 volts. Which means this current flowing up through this current source must be 0 amps. So these are identical representations from a circuit analysis perspective, right? For this particular value of Vx is 0 volts. Our current source behaves like it isn't even there, because that's what an open circuited current source does. It supplies exactly 0 amps of current, which means it contributes nothing to the circuit. And so by simply using good old Ohm's law, we can see that our Norton current, I Norton, is 10 volts over 5 ohms plus 20 ohms, or 25 ohms, which, let's see, so that's going to be 2/5 of an amp. Yes. If Vx is 0, then 3 times 0 is 0, right? Okay, so we have determined the Thevenin equivalent voltage for this guy. So whenever we have a dependent voltage source and we want to find the Thevenin equivalent voltage, what do? We find the open circuit voltage by literally any means necessary, okay? That's actually true whether or not there's a dependent source in the circuit. Then we found our Norton current. Again, really using any means necessary. For this particular problem, it was a series of logical steps that allowed us to simplify the circuit greatly. In other circuits, it might be using nodal analysis, it might be using mesh analysis, all that kind of good stuff. So our next step here is going to be determining the Thavinin resistance. And this is where things take a turn, okay? Now, the problem that we're going to have is that if we look at a dead network, we are going to have a short circuit here, a 5 ohm resistor here, our 3 Vx current source here. Sorry, should that be a 20 ohm resistor there? Here's terminal A, here's terminal B. And when we try to look into these open circuited terminals of our dead network, we run into a heck of a, because we no longer have just resistors, right? So we have to take into account, effectively, the resistance of this dependent source, which we don't have any real good idea how to do, okay? Let me redefine what Vx is here as well. So our options, we have a couple of them, okay? These are significantly less intuitive than some of the stuff that we've done previously in this class, okay? So our first option is to exploit the relationship between the Thevenin voltage and the Norton current, right? We know that the Thevenin equivalent circuit is the source transformation of the Norton equivalent circuit, right? And those two quantities are related by the following relationship, right? So we could say that our Thevenin voltage is equal to I Norton times R Thevenin, or I Norton is equal to V Thevenin over R Thevenin, or R Thevenin is equal to V Thevenin divided by I Norton, right? That's all just Ohm's law rewritten into 3 different configurations that we can come up with, okay? So we can see pretty easily here that our Thavinin is going to be -10/14 of a volt. So negative, let's see, 5/7 of a volt divided by 2/5 of an amp is going to look like -25/35. Is that right? 14, yeah, sorry. Now, we have what may seem like a little bit of a kerfuffle here as well, because our resistance turned out to be negative, all right? The reason that our resistance turned out to be negative is because of the dependent source, okay? So what do you guys think of, this will not occur for all dependent sources. It's just the way that this problem happened to work out. So we have not yet dealt with negative resistance in this class. What do you think negative resistance means? So what does resistance mean? Resistance is a constant of proportionality between current and voltage, right? So what we figured out like a month ago this marker isn't writing very well. Let me try it over here. I thought this was an it. There we go. Nope. Here is voltage. Here is current. We literally measured for a particular value of resistance the characteristic IV curve, where this slope was 1 over the resistance value. So as the voltage got positive, the current got, as the voltage got more and more positive, the current got more and more positive. So all a negative resistance means is as the voltage gets more and more positive, the current gets more and more negative. That's it. Okay. All of these fluorescent lights in this room work because of negative resistance. It has something to do with the ballast. I don't know what it is off the top of my head, but every single one of these fluorescent lights work because of the concept of negative resistance. So just because in this particular circuit, we have a negative value for the resistance, that shouldn't particularly scare us. It's going to happen occasionally whenever we have dependent sources, all right? Now, there is a way that we can determine the Thevenin equivalent resistance directly. And it also goes back to the fundamental definition of Ohm's law, okay? And so it's going to be applying what I call the test source method. So if we take our dead network, and to be clear here, anytime we are trying to find the equivalent resistance directly, we need to be looking at a dead network. If we leave any sources on, it will mess things up. So we have to be looking at a dead network. I cannot repeat that enough because that's a very common mistake that I see. So we have our circuit with our dependent source in it. Here's our 20 ohm resistor. Here's terminal A. Here's terminal B. Okay. So the test source method is simply we apply a test source to this network and then use Ohm's law to figure out what resistance the test source sees, okay? So that can be accomplished in one of two ways. We can apply a current source and then measure the voltage, or we can apply a voltage source and then measure the current, but we're just using Ohm's law. This is exactly what I talked about the other day during the review session when that student asked about that weird funky delta Y thing, or that, he didn't ask about a delta Y thing, but he asked about a resistor combination that couldn't be solved using traditional resistor combination techniques, okay? So let me make sure that I remember to include that voltage source Vx here. So what I'm going to do is I'm going to apply a current source for this particular problem. We're going to work it. So I'll show you how to apply a test current source and solve it successfully. And then I'm going to show you how to apply a test voltage source and then solve this particular system correctly, okay? So for our test current source method, what we are trying to determine is this voltage V test, where our Thavinin resistance will be the voltage V test divided by the current I test, which in this case happens to be 1 ampere. That's why I chose 1 ampere, okay? It actually does not matter what value of current source that I choose. I can make it 1 amp direction up, 1 amp direction down, 7/19 of a milliamp direction up. It does not matter. I choose 1 amp because it makes the math easy, right? Because I'm just dividing that voltage by 1, which gives me resistance, okay? So how might I go about figuring out what this voltage V test is? Exactly right. That by definition, that's what it is. But what circuit analysis techniques could I use to get there? Okay, no, that seems actually kind of reasonable. So the suggestion would be to do a source transformation on this practical current source on the left-hand side here. All right, let's see how that pans out. Seems actually like a good idea. I was going to suggest nodal analysis, but that might actually be better. So I'm going to have 3 times 5, so 15 Vx. Actually, this should be a dependent source. My apologies. And that's going to be in series with a 5 ohm resistor, right? Yep. In series with a 25 ohm resistor. Here's terminal A of my network. Here's terminal B of my network. 20, you're right, thank you. Here is Vx, which is exactly equal to the V looking for. And then over here is my 1 amp source. All right. So I've done a source transformation to make this guy behave like a single loop circuit. So what could I do now? KVL, okay? So I'm going to do KVL around this path. So that's going to give me negative 15 Vx And I'm trying to think of how to express this. Okay, so now that we have a single loop circuit, that 1 amp of current is flowing through everything, right? It's flowing counterclockwise around the path, which means we already know what the voltage drop over the 5 ohm resistor is, and we already know what the voltage drop over the 20 ohm resistor is. It's going to be 5 volts and 20 volts respectively. But we need to pay attention to the polarities. So this is going to be minus 5 volts and minus 20 volts, like so, because the current needs to flow into the positive polarity terminal to force those resistors to absorb power. Okay, so we're going to have negative 15 Vx minus 5 volts minus 20 volts plus Vx is equal to 0, which to me looks like negative 25 volts is equal to 14 Vx, and thus Vx has to be negative 14, no, sorry, negative 25 over 14. If I scroll up here, I have negative 25 over 14 volts divided by 1 amp gives me negative 25 over 14 ohms. I get the exact same result, but I didn't need to know V Thevenin and I Norton in this case. Okay, so the test source method really gives us a built-in to make sure we're calculating the Thevenin voltage and Norton current correctly, because if not, the ratios won't match up. Any questions about this before we move on to applying a voltage source? What's the voltage drop across the 1 amp source? It's Vx. I did. Right? So the voltage drop specifically over the 1 amp source has no relationship to, like the 1 amp source is supplying 1 amps of current regardless of what it's connected to. That's the fundamental issue when we try to take the voltage drop over a current source. But in this case, we can see directly that the voltage drop over the 1 amp source is just Vx, because the positive polarity terminal of Vx is connected to one terminal of the current source, and the negative polarity terminal of Vx is connected to the other terminal of the current source. So we did. That makes sense? Okay. All right. Any other questions regarding this particular one? All right. It's purely because there happens to be a dependent source and it worked out this way for this particular problem. So I would argue that if I change the direction of that current source, the resistance would wind up being positive. Only because there is a dependent source is a negative resistance possible. Okay, so it will not work that way every time. It just happens to work this time. And it's just the way that the numbers worked out. And we verified that that negative resistance was correct by applying the test source method and seeing that it gave us the exact same value, including the negative sign, that we got by just using the ratio of Thevenin voltage to Norton current. Okay, so that's what I was talking about, how we have a built-in means to check our answers here. For this part down here, I used positive on the right because I wanted my 1 amp of current to be flowing into the positive polarity terminal. So if I hadn't done that, if I had said positive polarity on the left, then the current that would have been flowing in would have been into the positive polarity terminal would have been negative 1 amp. So it would have worked itself out either way, as long as I'm applying Ohm's law correctly.
also flip the current, so.
Well, so I applied my Kirchhoff's voltage law equation following that blue line in a clockwise fashion. But if I understand that that current 1 amp is flowing in the opposite direction, that's why I would get negative currents if I had put the positive polarity terminal on the left. Now I could just as easily work this problem with the 1 amp current source direction down and wind up getting the exact same result. The polarity of my test voltage sources and the direction of my test current sources are completely inconsequential. I can choose whatever makes the problem easier for me to work. You'll get the same answer every time. Let's look at a voltage source, a test voltage source in this case. Oh, sorry, we didn't have a 15Vx source to begin with. My apologies. So what did we have? 5 in parallel with 3Vx. So we have a 5 ohm resistor. A 3Vx current source. 20 ohm resistor. Here's my terminal A. Here's my terminal B. Now I'm going to apply a test voltage source, right? And just to recap here, this is my voltage Vx, okay? So when I apply my voltage source, I get to decide on both its magnitude and its polarity. So I am going to choose 1 volt, positive polarity on top. And so to be clear here, my expectation is that the Thevenin resistance will simply be the ratio of V test over I test, or my test voltage in this case is that 1 volt source. So what I'm looking for is the current flowing out of the positive polarity terminal of my test source. Now, what did using a test voltage source do for me in this particular problem? It won't happen for every problem, but in this particular problem, a test voltage source helps us out. Any thoughts as to why? Exactly right. We get to define what Vx is, which means our dependent current source doesn't really behave like a dependent source at all. We know that that current source will now supply exactly 3 amps of current. It's very well behaved, pretty trivial to deal with. All right. So how would you like to analyze this circuit and determine I test? Jenny, you've been quiet today. I'm going to pick on you. Literally just throw something at the wall and we'll see if it sticks. So what we did before using a source transformation, okay, let's see how that pans out for us. So doing that same source transformation is going to give us sorry, that shouldn't be 30, it should be 15. Can't do simple math today. So here's 5 ohms, here's 25 ohms. Dang, it's 20. I keep doing that. I apologize. Thank you. All right. So our goal here is to figure out what I test is. Now, as Kyle, I believe, mentioned, we know that Vx is exactly 1 volt because we put a 1 volt source there, which means that this is just a 15 volt source. So if I want the current flowing around this single loop circuit in the counterclockwise direction, what do I need to do? Caitlin, thoughts? Ohm's law, all right. So, well, so explain what you mean by Ohm's law, Joy. Okay. Okay. 100% correct. So what should it look like? Okay. So I would argue that since we're following the current counterclockwise, I have 1 volt minus 15 volts. So it's going to look like negative 14 volts combining the resistances gives me 25 ohms, and I'm looking for this current, so I can easily see that it's negative 14 volts. Did I get this backwards somehow? Oh, no, I didn't. Negative 14 volts over 25 ohms. So my test voltage 1 divided by negative 14 over 25 gives me that same resistance of negative 25 over 14 ohms. Right. So let me write that out here. VTH is going to be 1 volt divided by negative 14 over 25 ohms. Sorry, amps. Current is measured in amps. 14 volts over 25 ohms. Dang it. Gives me negative 25 over 14. So 3 different ways we got the exact same value. I feel very, very strongly that we did it correctly. Okay. So that's the test source method. On this in-class assignment, on the back page, is a circuit that I ask you to find the Thevenin resistance of, and it contains no independent sources, right? So if it doesn't have any circle sources, the only way you can do it is using the test source method, okay? Because you have no live networks by which to determine V Thevenin and I Norton, all right? So I'm going to pass these out. I'm going to give you guys a chance to take a crack at them. If you have any questions or anything, I'm more than happy to answer.